Hello and welcome to this presentation on high-fidelity agglutinate simulants. This was done in partnership with the XLF Lab at the University of Central Florida, as well as the Center for Lunar and Asteroid Surface Science. My name is Parks Easter, and I'm an undergraduate at the University of Central Florida studying civil engineering. I am also the lab manager at the XLF Lab. So to get started here, I'm going to give some background on lunar agglutinates. Agglutinates are glassy matrices of melted regolith caused by micrometeorite bombardment on the lunar surface. Essentially, over the last thousands of years, micrometeorites have impacted the moon's surface, rapidly heating the regolith and then allowing the regolith to cool in the vacuum of space. This forms these super weird shapes as seen on the right in Apollo 17 sample 71515. This is a lunar highlands agglutinate and shows just how weird the shapes of the agglutinates are and how it changes the properties of the regolith. These agglutinates make up anywhere from 5% to 65% of the lunar regolith composition, increasing with maturity. So a younger soil would have somewhere from 5 to 20%, and the oldest soils have about 65% agglutinate content. Agglutinates are important because they affect many aspects of the lunar regolith. For example, particle geometry, magnetic susceptibility, and mass flow rate. And we'll see why those are important in a later slide. So the implications of agglutinates within ISRU. The percentage of agglutinates within lunar regolith is going to vary from site to site on the lunar surface. So wherever NASA decides to go on the Artemis missions or private industry decides to go, there's going to be different amounts of agglutinates wherever you go. ISRU processes will need to take into account the mechanical property changes caused by the mineralogical and agglutinate percentage variation, as they will not remain static. Many technologies are being developed for use on the moon that will process the regolith, as the regolith is really our most valuable resource on the moon and will undoubtedly be used for any lunar economy. Some of these include molten regolith electrolysis, water extraction robotics, and in situ lunar infrastructure. Most of these ISRU processes will require knowledge on the characteristics of the regolith before they use them, such as mass flow rate and shear strength. Shear strength is essential really for any sort of construction, as any geotechnical analysis or construction processes will need it. And really anything transporting regolith or utilizing it will need to know the mass flow rate, as they'll have to move regolith from location to location within the system. See on the right here is just a model of in situ lunar construction and how they'll likely utilize this regolith on the moon. So to give some background here on the simulation of regolith, the XLF Lab simulates both lunar highlands, or LHS-1, and lunar mare, or LMS-1 regolith. Some of the characteristics that are simulated are mineralogy, chemistry, particle size distribution, volatile release, and the derivative properties such as spectra. While many aspects of the regoliths are simulated, agglutinate content has historically proved extremely difficult, as it is very energy intensive, and while it can be replicated, it's often too expensive to realistically use in bulk amounts of regolith. The regolith simulants are essential tools in testing space hardware on Earth, and many companies utilize them before they go up into space, as lunar regolith erodes and has the potential to destroy equipment, as seen on the Apollo missions. It's really one of our biggest challenges and biggest resources on the moon. And a higher fidelity simulant ensures more accurate results, and more accurate results are really what you want before you go into space. Seen here on the right is NASA's Viper rover, which is going to the moon, I believe, in 2025, and it's being tested in lunar regolith simulant. XLF is actually providing some lunar regolith simulant as well. So this just shows how the simulant is utilized on Earth before the hardware goes to space. So to talk a little bit about the agglutinate simulant, the XLF Lab has developed a methodology to produce simulated agglutinates using a solar concentrator. This keeps the price low and the process fluid. What it does is it replicates lunar agglutinate mineralogy and glass features. The simulated agglutinates consist of 99% anorthosite and 1% fine metallic iron by weight. This iron is added to replicate any magnetic properties that lunar soil would have. Ideally, what this does is it increases the fidelity of the simulant while keeping the cost affordable and accessible to the scientific community, because if you can't test on Earth with these bulk amounts, there's really no use. So what we've done to make the simulant, simulated agglutinates have been added to the Lunar Highland simulant at 25% by weight, which is why the simulant is named LHS-125A. What it does is it simulates a moderately mature Lunar Highlands regolith. What it doesn't do is it does not simulate nanophase iron or ferrocastle structures, as we are in 1G gravity and Earth atmosphere. Eventually, it will be possible to order all sorts of different percentages. You can actually request a custom percent right now at Exolith, at the Exolith website, as well as you can request just agglutinates if you would like. It's also important to note that this is still in a preliminary testing phase, and while you can order it, it is by no means perfected in any way yet, but is getting better every day. You can see in the picture in the top right, this is some agglutinated LHS-125A simulant, and the larger black structure on the left is the source material. So this is what the agglutinates look like directly after melt. You can see in the bottom right as well, here's the source material up close. This is what it looks like, and then it is crushed and added to the simulant to form a more realistic mixture. So the methodology in which this simulant is created, an orthocyan iron mixture is melted with a solar concentrator, welding unmelted lithic grains into the melt, just as they would on the moon. Methods to increase the accuracy of the simulation, such as quenching of the agglutinin after formation, are currently being explored and added as we learn more. This is important because on the moon, the agglutinates really rapidly cool in the vacuum of space. This is really hard to fully achieve in Earth's atmosphere, but quenching them hopes to get us closer to the accuracy of the actual agglutinates. These agglutinate pieces are then crushed and passed through a 500 micron sieve. This powder is then added to LHS-1 at 25% by mass. The reason we pass it through this sieve is to match the overall distribution of LHS-1, which is meant to replicate the Apollo samples and just sort of average distribution of the lunar soil. So we want it to be as realistic as possible, and this is our way to achieve that. Here on the right-hand side, you can see some simulated agglutinates undergoing crushing. This is in a mortar and pestle. To the right of the mortar and pestle, you can see some of the source material. To the left, you can see the actual pieces undergoing crushing. These are not less than 500 microns yet. These are still significantly larger, but that happens over time. So some analysis of the simulated agglutinates. The simulated agglutinates have already undergone thin section analysis, and visually the simulated agglutinates appear to be similar to lunar agglutinates, which is a great sign for the preliminary research. On the left-hand side here, you can see this is a simulated agglutinate thin section put through transmitted plane polarized light. On the right-hand side, you can see an actual lunar thin section of an agglutinate, specifically 68501. And you can see here the grains are similar, sort of the grain distribution, as well as the pockets of air that are contained within the agglutinates. Some of the mechanical property tests that have already been done on the agglutinates are flowability, which is shown here below, or mass flow rate. What we did is we compared it to LHS-125A to LHS-1 to see if adding agglutinates to the mixture changes anything. What this data shows here is that there is a significant difference in the mass flow rate between LHS-125A and normal LHS-1. This supports the hypothesis that the agglutinate content affects the mechanical properties of the lunar soil as we expected. I just want to make it clear this is extremely preliminary data. and we'll be working more with it to get more data and more accurate results. One interesting finding here, as you can see on the chart, is that the mass flow rate of 25% agglutinate mixture is actually higher than the normal LHS1, which is not as expected, as ideally adding more glass should slow down the flow rate, as the shape of the glass keeps it together more. But what this does, as we perfect the process more and more, it allows simulants to be developed for specific sites on the moon with maximum fidelity. So if there is a site chosen to test MRE or ice extraction, we can develop a simulant with the exact percentage of agglutinates that we need, and that can be used within the test to be accurate to the maximum degree. Some further testing that's going to happen with these agglutinates is shear strength testing. This is the next geotechnical test that the simulant will undergo. And SEM analysis is occurring in the upcoming weeks to see if the shape matches the shape of the agglutinates found actually on the moon. Eventually, LHS1 with varying percentage of agglutinates will also be tested in order to quantify relationships between the agglutinate content and the geotechnical properties of the simulant. So, for example, 10% agglutinates, 20% agglutinates, 30, 40, 50. And with that, we would actually be able to quantify the relationship. The analysis that we've done here is mostly qualitative and is good preliminarily, but further research will need to be done to confirm any results or how exactly the simulated agglutinates affect the soil or regolith ultimately. You can see on the right-hand side here, this is some of our LMS agglutinate source material. It's currently a prototype, and whereas in LHS we use only an orthocyte to simulate the agglutinates, due to the complex mineralogy of LMS, we have to actually agglutinize the entire soil. But that accurately simulates how it would occur on the moon as well. Just want to give some acknowledgments here. Thank you to our amazing team at XLF in class, as well as those who have supported us in our mission to further space exploration. I have absolutely amazing mentors that have helped me along this process, and an amazing team of people that developed the solar technology and the agglutinate process. And it's just super exciting to be able to work on this kind of stuff in my undergraduate degree. This work was also made possible through NASA Cooperative Agreement 80NSS C19 M0214. So thank you to everyone. You can contact us at peaster@knights.ucf.edu or preferably at xlflab@ucf.edu with any inquiry on receiving some agglutinates for testing or receiving a simulant or any simulant needs in general. Thank you so much.